schedule changes. So if you have your schedule, which is on the last page or the next to the last page of your syllabus, if you could pull that out or make some kind of notes for yourself, depending on how organized you are. So Friday, we're supposed to start transformations of functions. And notice I've dedicated 3 days to that, which is a pretty significant chunk of the semester. I really don't want the first day of transformations to be broken up by a long weekend. Since we don't have class on Monday, it means we won't be seeing it again to next Wednesday. So since the class that we would have normally been doing a week from Monday, combining of functions and composite functions, does not depend at all on transformations of functions, I'm going to move this class, combining functions and composite functions, which is section 2.6 in the book, to this Friday. And that way next week we'll have Wednesday, Friday, and then the next Monday all on transformation of functions. Okay? So all I'm doing is taking this and switching it for Friday of this week. The other thing I'm going to do is I'm going to move quiz 6. Now this is a long way off, and I'll remind you, from Friday, October 25th to Monday, October 28th. I'm just going to move that quiz forwarded. Huh? It does? Really? Oh, cool. Oh, I switched those around? Yeah, well, we'll see what's happening. So I have it this way on yours? Okay. I looked at my draft schedule, so okay. Good. So Friday will be section 2.6 instead of transformation of functions. And then nothing else is switched since you already have it anyway. Okay, good. So today we're going to start a topic that's near and dear to my heart, linear regression. It's the first type of regression that we're going to be doing in the class, formally doing. We're going to be looking at quadratic regression and polynomial regression later on. And we've already had a sense of regression without actually giving it the name. If you recall, in our very first project that we had for the semester, we were looking at an equation that modeled a linear equation right here, y equals 385x plus 3129. And that equation was supposed to model the cost of tuition and fees for U.S. public colleges, okay? From, I think it was the year 2000 to 2010 or something, 2010, okay? So whenever we try to determine a relationship between two quantitative variables so that one of the variables can be used to predict, and when I say predict, that means you're going outside in either direction of your data set. You're either going further into the future if it's like this situation, or into the past. Or estimate is when you stay within inside your data set. Okay, so you're either going to use one variable to predict or estimate the other. This is what we call in general regression. And regression can be linear regression, quadratic regression. We can have a quartic, like a 4th degree regression. We can have logarithmic regression. Okay? We can have all kinds of regressions. I was meant to say logistic. Anyway, in today's class, we'll look at the simplest form of regression, which is linear regression. Okay, that's what we're going to do today, because a straight line is the simplest model that you can get. All right, so let's take a look at the first table. So table 1 gives a nationwide infant mortality rate for the period from 1950 to 2000. Okay, so it's every decade between 1950 and 2000. The rate, how they calculate the rate, is the number of infants who die before reaching their first birthday. That's the infant, because they're still considered infants, out of every 1,000 live births. So just take a look at the data for a minute. And anytime you're looking at real world data, you want to just look it over. And in a minute, we'll be graphing it. But then you want to ask yourself, does there appear to be a relationship between the two variables here, which is the decade that we're looking at, 1950, 1960, up to 2000, and the infant mortality rate. Does there appear to be some type of relationship? Yes, no? Jonah? Okay, so he's saying yes, there does appear. Yes. And Jonah says, how would you describe this? He says the U.S. infant mortality rate appears to be decreasing. Or he said is. So let's make that statement more positive, more certain. Is decreasing as time goes by. Okay, so this is decreasing as time goes by. Okay, so no fancy language, right? He's just noticing that as time goes by, I kind of like that. There's an old song called As Time Goes By. Anyway, as time goes by, the infant mortality rate is decreasing. Okay, that's it. It's often very useful for us, you know, a picture is worth 1,000 words, right? So to get a picture of the data. So you can then graph these two quantitative variables. And when you graph real data like this, we call this type of graph a scatter plot. That's the name that we give to it. So you can't see the axis on my screen, but on your paper you have the axis. And what is your axis? What is the y-intercept? What does it start with? 0, right? So, and then the next one's 10, 20, 30, 40, and then 50. I guess am I 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5. So I'm all set. All right. Now notice here, I don't have 1950, 1960, 1970. What am I using for my x variable here? If I got 0, 10, 20, 30, 40, 50, Brendan?
Years after.
Right. I'm saying let x be the number of years after 19 or since 1950. So 1950 is going to be 0, so that's your y-intercept. So that's why the very first data point appears on your vertical axis here. Okay, so then when you kind of look at it, you say, you can say, okay, that kind of totally verifies what Jonah was saying, that as time goes on, there's a decrease in the infant mortality rate. And so overall, you look at your picture and you ask your question, does there appear to be a pattern or a trend to the data? And you might say, well, how is that different than what Jonah just said? Well, you could repeat what Jonah just said, but you also might use some other language now if you want to talk about that picture versus the data as a numerical table. What might you say now as you're looking at that picture? Anything you want to add to that about the pattern, Julia? Right, a negative trend. So let's look at that word, negative trend. And in just a minute, we're going to use the word association instead of trend, but trend is fine. So I'm just going to put in here association. There's a negative trend or a negative association between your two variables, between the number of years since 1950 and the U.S. infant mortality rate. Okay. Yep, there's a negative trend. That's just another way to say what Jonah said, which is some different language. And here you can say, you can notice that as your value of x is getting bigger and bigger and bigger, what's happening to your y values? They're decreasing. So as one variable is increasing, the other one is decreasing. They're working in opposite directions, okay? What about the picture itself? What kind of form would that picture have if you were going to try to graph it or put some kind of graph to that? What form do you think it might have? Kind of trend in terms of a graph. I mean, you can't, there's no perfect graph for this, because it doesn't follow a formula. This is real world data. Nothing lines up perfectly. So overall, what might you think in terms of some type of picture that would try to capture the essence of this negative trend? What might you do here? A lot, well, that's eventually where we're going, the line of best fit, right? So a line, right? This has some kind of linear trend to it, okay? And so do you think that so here's what I want you to do right now, and we'll get to this idea of how strong this is. Draw a line through the data set that you think visually best fits the data. And so there's probably going to be as many different lines as there are students in this classroom right now. So you just ballpark with your pencil and use your studio bookmark if you want a little ruler and just eyeball what you think might be the line of best fit here. Okay? And what we mean by that is a line that lies as close to these points as possible. Sometimes it might go through an actual data point, sometimes it may not. Okay? Has everybody drawn a line through? Okay. So the other question we want to ask, and we'll get to this line in a minute, is how strong do you think the relationship is, the linear relationship is, because that's what we've decided. I'm going to just throw a line in here just to, in the days before technology, I used to have an overhead and I used to bring in a piece of pasta and put it on the overhead. Students would come up and put their piece of pasta on the data set. It used to be kind of fun, but it made me hungry. No. Okay, so let's say that's where I'll put my line. May not be the best line, but it's some type of linear relationship. Okay. So how strong do you think the association of the trend is between these two variables? Strong. And someone said very strong. So we've got a strong and we've got a very strong. Okay. And what sort of like intuitive notion are you using? And I'm going to put in here linear relationship. Now that we've established that we want to put a line through there. What kind of intuitive sense are you using to say that this relationship is strong or very strong? Sonia? Okay, so you're actually looking at the line that you drew through your data, and you're seeing, wow, some of the points actually lie right on the line, and the ones that don't, they're not too far off. They're pretty close, right? So that gives you a sense that there's this really strong relationship going on, right? There's a chemical attraction. No, I'm only teasing. All right, I got to remember I'm on YouTube. All right, so let's take a look at the next thing. All right, so Nathan, you want to read us this, please? I forgot an A there. We have a statistical method, right? So we have a statistical method that's going to determine the one and only one line that best fits this data. It's called the least squares regression line. That's the fancy name for it, the least squares regression line. Some people call it the line of best fit. Some people just call it the regression line, okay? And you'll see these used throughout the lecture notes. I've just kind of, sometimes I'll use least squares regression. Sometimes I use line of best fit. You can use them interchangeably. You can interchange them, okay? So a lot of, you may not care or wonder, but some people say, why is it called the least squares regression line? And I'm going to try not to go into like a statistics mode and explain it all to you, but I thought a picture would help you understand least squares. So what kind of picture comes to your mind when you think of the word squares? A square, right? And we're trying to find a line that's as close to these points as possible. So if you imagine that I literally draw a vertical distance from the piece of data right down to the line. So if it's below the line, I draw a vertical line up to the line. And when it's above the line, I draw a vertical line down to the line. That distance represents, right, how far each data point is from the line. Okay? So we want to minimize that. We want to make that distance as small as possible. And since the distance could appear to be positive here, if the point is above the line, that distance is positive. And here, if you subtract your value from the estimated value on the line, it would be negative. So you've got to undo that positive and negative. So some people say, well, if I square a number, it will all be positive. And what they literally do, what this method literally does, is it takes this distance and it makes a square from that distance. So for example, if that distance was like, just for example, 1 unit, this square would have an area of 1. If this distance was 2 units, this square would have an area of 4. And this line, the least squares line, minimizes these squared distances. There's no other line, whereas if you put these little squares these little squares, which are formed by taking the distance from the point to the line, there's no other line that will have a sum of squares smaller than that. Okay? So the sum of all these squared areas for this particular line, just in case you want to know, is 10.89. So there's no other line that will make an area smaller than that when you add up the areas for all the squares. And that's how they form the least squares regression line. Now, you don't really need to know all that, but that's the theory behind it. That's the statistical theory. Okay, so that's why it's called the least squares line. Okay, so in general, if we're going to be talking about a pattern that we notice on a scatter plot, and you'll have this question on your project for due next Wednesday, you always want to discuss it in 3 ways. You want to say, what form does it have? In this case, the form is going to be a line. Sometimes the form might be a curve. You might look at data that curves. You might look at data that increases and then maybe reaches a plateau. Okay, that's later on. At the end of the year, we'll be looking at logistic growth. Okay. And you also want to say, well, what's the direction of my data? And as Julia said in Jonah, they've noticed that this particular data has a negative trend, association, or direction. And then the strength of the relationship is what we just said, strong, very strong, and that was an intuitive feel. Okay, so we're going to discuss direction and strength more formally in the next few minutes. Okay, Brendan, you want to read this for us?
Define the direction of a relationship by looking at the two variables of a positive and negative association. We say that 2 variables are positively associated with a larger value of variable or larger values of another variable, and negatively associated with larger values of variable or smaller values.
Okay, so I've lost one of my data points here, I think, yeah, because when I copied from my Word document up to Notebook, I've lost one. So we've already established this. We've already established without even getting here that these variables, these 2 quantitative variables, are negatively associated. There's a negative trend. So we've already discovered that without even getting to this part. Okay, and that sort of fits our notion of the slope of a line, right? If it's negative or positive, it's the same idea. If your line is decreasing as you move left to right, it's a negative association. If your pattern is increasing as you move left to right, it's a positive association. Okay, we can't rely on our eyeballs here to figure out the strength of this relationship, because you can change. I mean, there's all these books written, and there's these books on visualizing data where you can actually take data, and by adding a lot of white space around it and changing the scale, you can take something that looks very linear and make it almost look like it has no relationship. So we need to have a mathematical way of measuring the strength. So what Orlando and who else said it was Orlando said strong and someone said very strong. I just heard, was it Julia or Liza who said very strong about 10 minutes ago? Okay, so Julia and Orlando said, hey, we think this is a strong relationship or a very strong. Well, let's calculate a measure mathematically that will help us determine how strong that is. Okay, and that's what we call a correlation coefficient. It's a mouthful. Okay, correlation coefficient. You want to know how well the 2 variables are correlated. Okay, so Cecily, you want to read this for us? Okay, so we have two graphing utilities we're using this semester. Your project is going to show you how to do all this with GeoGebra, and today's class will focus on how to do all of what you're doing with GeoGebra with your graphing calculator. So you'll always have two methods available to you. The good thing about GeoGebra is it's free. You can download it and you can have it for the rest of your life. And I know you always want to be continuing to use GeoGebra for the rest of your life. But no, really, I'm serious. If you transfer to a 4-year school and you have projects to do that require any kind of data manipulation, you'll always have GeoGebra in your side pocket. Okay, so let's take a look at the correlation coefficient. Again, it's measuring the strength of the linear. I should have probably put that in. It's measuring the strength of the linear relationship or the linear association. That's all baby R does. Talks about the strength of the linear relationship. I can't emphasize that too strongly for you. Okay. So one question I would have is, what do you think an R value of 1, -1, and 0 would look like if you were looking at data? What would a correlation coefficient of +1, -1, or 0 look like? So I gave you some graphs to look at. And does anybody have a sense which one of these might be +1? Orlando? The first one, right? +1 says there's an exact linear fit. This is like those equations when we say y equals 3x plus 2 and you graph your line. There's an exact linear fit. I wouldn't say it's impossible, but I have seen data sets where the correlation coefficient is like 0.99. It's really close to 1, but there's a little variation. So this is almost a theoretical thing when you're dealing with real world data, to get a +1. But this just says if you have your data points and they're lined up exactly in a straight line with a positive slope, then your correlation coefficient has a 1 for a value, a +1. So if we look at the next picture, our guess would be what for a correlation coefficient? -1, right? So it's intuitive in that sense because you've done a lot of work with slopes of lines. Okay, so notice the sign of your correlation coefficient, positive and negative, tells you what direction, a trend, or overall association you have between your two variables. The magnitude, oh, I know that's going to come out loud when I hear it on the magnitude, which is just your absolute value of these numbers. You don't pay attention to the sign, tells you how strong it is. Okay, so they both have a magnitude of 1. Okay, it tells you that this is as strong as you can get. These are your outer limits. You can't get any stronger than 1, +1, or -1 for your correlation. So the sign tells you the direction. The strength of the relationship comes from its absolute value. Now, here's some data over here, and you look at that and you say, okay, it's got to be a positive direction. As one of my variables is increasing, so isn't my other one. So I'm going to have a positive association going on here. And I don't know yet what my R value is, but I do know my R value has to be between 0 and 1. I know it's not equal to 1 because they don't lie in a straight line, and I'll show you why it's not equal to 0 in a minute. But there's going to be some R value between 0 and 1. So it's going to be a decimal between 0 and 1 that's positive. Okay? And similarly, if we go in the other direction, if there's a negative association or correlation, as the X increases, the Y values decrease. And the fit is not exact like in the first two diagrams. Now this last picture, notice it's almost like you could put a circle around that data, right? It almost, if you were, so like here, if I kind of encapsulated, this data, I'd have this sort of like cloud of points that formed a linear pattern. Whereas this, if I put, it's like a circle. I could draw a line in any direction through that. There's no way I can capture any trend there because there isn't a trend. So this is a situation where we say the correlation is close to zero or zero. Okay, there's no correlation at all going on. Okay, there's no tendency towards making a linear pattern in any way. That I was just putting that blue box in there, Curtis, because when I clipped this table, they actually had the R values in there, and I wanted to discuss that with you without you seeing it. Okay, so I just covered them up. Is that what you were asking, Curtis? Okay, all right. So here's our question. Go look at our data, our infant mortality data. And what I want you to do is make a guess. No one's going to look. You can cover up your paper. Make a guess as to what you think the R value is for our data. Okay, so we have a scatter plot of those 6 points. Okay, as time goes on, so what do you think your value of R is? Just write it here, record your guess. And if you don't mind, I just would like to record some guesses from class, what you think it might be, if you're willing to be brave and put yourself out there. Okay, Brendan? 0.95. Okay, someone else? Julia? Negative 0.85. Okay, yeah, someone else? -1. Do they lie exactly in a straight line, Sonia? Is there any deviation from the point and the line? Okay, so it can't be negative. So what would? 7, okay. Ryan? Negative 0.73? Okay. All right. Okay, you want to make one, Orlando, just to get in there? No? Okay. All right, so we'll come back to this in a minute. Okay.
I'm curious, is there a way to figure it out?
Yes, your calculator is going to do it.
Oh, all right.
Okay. Okay, so now how do we actually calculate? Okay, we started this lecture off by saying we've already used a model to look at the cost of tuition for U.S. colleges. From the very first day of class, we had this linear model. Y equals 385x plus 3129, where Y was what we were saying is the cost to attend a U.S. public college, X was the year, okay? And this was the model they gave us. This is a line of best fit. They didn't tell you this, but this is a line of best fit. If you go back and you take that data from that picture I gave you in the first project, and you do what we're going to do today, you will get this line, this equation. Now, I want to do something only because I was trained in statistics. My master's is in biostatistics, and I can't stand seeing linear regression models with Y there. I want you to put a little caret on top, a little hat. Okay, so every time you write a regression equation or any regression equation, linear or otherwise, put a little hat, dress it up, okay, on the Y. And what that tells you is that this is a predicted value. Okay, it's being predicted. Okay, it's not an exact fit, it's a prediction. So I would just like you to come away with that little bit of like statistical knowledge that you're going to put a hat on these Y's. Will I take off of that if you don't do it? Absolutely not. But just to make me happy, if you're interested in making me happy, that would make me happy to see little hats on all the Y's, okay? All right. Yeah. Okay. So the only way we can actually find the least squares regression equation or the equation for the line of best fit is to use calculus. Okay, well, the good news for us is that our calculators, our GeoGebra will do that for us without knowing the calculus behind it. Okay, so if you go on and you study more mathematics and you take an upper level stat course at a university after you've had calculus, then you will actually see how to get the least squares line. Okay, so now what I'm going to do is I would you can take out your calculators, but I don't want anybody to do anything yet. Okay, because these steps, I just want you to see the steps once. And what happens, and I've been doing this class for a long time, is if I try to say, okay, let's start together, people go on, people get stuck, people then, like I'm 3 steps ahead and people ask me a question from way back, blah, blah, blah. So I really would prefer that you just watch me go through it once. It took me hours to write all these steps down for you, so they're there. You'll always have them to go back to. If when we're working with the real world data in like 5 minutes, you have questions or you're not following something, I will be by your side. But I just want you to watch the process. How do we enter our data into the calculator? How do we get a scatter plot? How do we come up with the line of best fit? We don't have yet the line of best fit for this data, and we don't yet have the correlation coefficient R. We've made guesses. So I'm going to call up my little calculator here, and I'm going to try to follow my own steps, and I took pictures from my calculator screen and embedded them. Thank you, Linda. You're so kind to spend all that time and think of us. Oh, you're welcome. Okay, so I talk to myself all the time. All right. So the first thing, even though it's going to be the last note on your lecture notes, is to get all of the information you need, your diagnostic must be turned on. And I've written down how to do this. I just want to show you. This should be the first thing you do when you use your calculator for the first time. So your diagnostic, you go down to, and I'm just going to show you, don't worry, it's all written down, second catalog, and unfortunately you do have to scroll all the way down till you see diagnostic, which begins with D, diagnostic on, thank God it's not a Z. So you go up here, you hit enter, and then you hit enter again. And now when it says done, that means your diagnostic is on. Okay. So that's the one thing you want to do before you start any regression equation or any kind of scatter plot or anything. Okay, so we're done with that. All right, quick. Okay, so we've got 6 pieces of data to enter, right? We've got the years since 1950, and then we got the actual infant mortality rate. So the first thing I do is I hit my stat key because I'm in my stat mode. I'm going to edit my lists, and then you see a bunch of lists on your, oops, I have to reset these to L1 and L2. I got to remember how to do that. Stat, setup editor, enter. Okay, stat, enter. There they are. Okay, so I've got to clear out these lists because this is old data here, right? I got to clear out the lists. So, and then I go up to L2. Don't hit delete because it will take away your actual L1, L2. You can get it back like I just did. So don't freak out. You can get it back. So what am I going to put in for L1? 0, 10, 20, 30, 40, 50. So you just enter it like you normally would enter. 0, enter, 10, enter, 20, enter, 30, enter, 40, enter, and 50. So we're using the years from 9, and then I'm going to cursor over with my right cursor. And could you read me the infant mortality? I think the first one's 29.2. Is that correct? Yes. And then a 26, right? Yes. I almost got this data memorized. And then a 20, right? Yes. Is the next one 16 something? 12.6. 12.6. Okay. And then a 9 something? 9.2. And the last one? 6 what? 6.9. Okay. So I've entered my data, and here you can see it right on your screen. Okay, there it is, exactly what I've just done. Okay, now second I want to graph this data. Okay, so I press my second equals key, y equals. My second y equals key means I'm going to get what's right above it in yellow. Right above it in yellow you see stat plot, because I want to plot a scatter plot. So I hit second stat plot, and I'm going to, you notice you can plot 4 different statistical plots here. So we're just going to go down to the first one, and I'm going to turn it on. And notice it says plot 1 is on. So after we do this linear regression and you're back to just entering regular old equations into Y1 and you get a dimensional error, it's because you forgot to turn off your plots. That will happen, I guarantee it. Okay, so we go down You have all these different types of plots. So if you take statistics, you'll learn about box and whisker plots and histograms and all this stuff. But the very first picture here is a scatter plot. So then you just keep going down. Now, this says my independent variable is being taken from L5. Well, no, it's taken from L1. So I got to come down here and tell my calculator L1. So I hit second 1, and there's my L1 right there in yellow. And then my other list of data, my other data values for the infant mortality rate is put into L2. And then you can use either little squares, pluses, or dots for your graph. Okay, so we're done. Okay, we're done with that. Now, if you want to get the plot right now just to look at like you haven't seen the data, you hit zoom, and then you can just hit 9, but I want you to see zoom 9 is your statistical zoom. So once you hit that, you'll get a graph. Now look, I got a line there. Why do I have that line there, do you think, or this thing? It's in the y equals. See, I had x cubed in there. I never shut it off. So if you get something funky, that's why. Did I just shut that off? No. Let's clear that out. Clear it out. Okay. So now when I hit graph, I should just get my scatter plot. There it is. So we're halfway home. We've got the scatter plot. You notice the trend. Okay. Our goal is to get the line of best fit going through there. So let's see how we do that. Okay. So third, we want to find the line of best fit. So this is how we do it. We're going to hit our stat key again. Stat. And now we actually want to calculate the line of best fit. We want the computer to do all that calculus we just talked about. And we come down here to number 4 where it says REG, linear regression. So we come down here. Okay, we got to scoot over to calc, and we come down to number 4. We hit linear regression. So the calculator says to you, what two lists of data, what 2 data sets do you want me to do this linear regression on? Where did we put it? In L1 and L2. So you tell it, I want you to do a linear regression on L1, and then you got to put a comma. And I also want my second set of values is in what we call L2, and then you put a comma. Now, why do we put a comma again? Because you want your linear regression line to show up on your graph. And in order for that to show up, it has to be put into Y1, because that's how you graph stuff. You go to your Y equals button and you put equations in there. So when you tell the calculator it's going to do all this calculation and give you this information, you say, I want you to put that information in Y1 so I can get a graph. So to do that, this is a new button now, and I've written this all down. You go to vars. You go over to the Y variables, Y vars, and you say, enter. I want you to appear in Y1. And you hit Y1. Now you're all set. You hit enter, and there's all your data. Notice they have your line in MX plus B form, but instead of M and B, they call it AX plus B. This is your A, negative 0.4837. That's your slope. Your Y-intercept is 29.4. And what's the R value? Not the R square value. What's the R value? Negative 0.98. Negative 0.9868. Very strong. Okay, so, okay. And then finally, now when you look at your graph, oh, something happened to my calculator. Where did it go? I don't want Sketchpad. It's down here hiding somewhere. I've scooted it down. Come on, I don't want to close it. Get up there. There we go. Oh, no, did I lose everything? I think I did. Anyway, I did. So then when you go to your graph, you'll actually see your line of best fit. Okay? So all the steps are there. You have a ton of, I want to do one problem with you. You have a ton of data sets to work on, okay, for the rest of the period. But let's use our regression line to actually estimate the infant mortality rates. So what is our regression line? Here it is right here. Y hat equals negative 0.48x plus 29.4. So we're going to use that line. Y hat equals negative 0.48x plus, what was it? Do you have it right in front of you? 29.4? so I don't have to go back. So I got everything right here. That's a 0. Can't be a 6. Well, it could be a 6, I guess. Okay. Okay, negative 0.48x plus 29.4. That's our line of best fit, the equation for our line of best fit. We want to use this regression line to estimate infant mortality rates in 1995. Why am I using the word estimate versus predict? Did you catch that at the beginning of the class when I said it? We're already past 1995, and your data goes from 1950 to 2000. So 1995 is halfway between the two decades, 1990 and 2000. So we know what we were in 1990, and we know what we were in 2000 for an infant mortality rate. So when you are finding the value with your regression line, your linear regression line, for a value that's within your data set, that's called interpolation. Interpolation, it's a big long word. We're interpolating. So that's where when you use your estimate. Okay. So what do I put in here for X now? I forgot how we do this. 1995 minus 1950. Yeah, because that's going to give me the number of years from 1950, right? Which is going to be a positive 45. So that's my X value. So I go in, and where I see X, I'm going to put 45. I'm going to multiply it by 0.48, and I'm going to add 29.4 to it. Well, if I didn't lose my calculator, I could have just gone to my table, because I already got Y1 in there, and just put in the number 45 and saved myself a little bit of work. But I'm going to have to do a little, oh, look, maybe I still have it here. I got 2 of them there. Oh, come on. Let's see if it's this one. Yes. Okay. So what I mean is I can go to my table, and what am I interested in? 45. So I can just set, I got to make this a little bit smaller. Woohoo. All right. Well, I got to make it a little bit smaller. Woohoo. All right. So we're going to start at, let's start at 40, and we're going to increment by 5, so I can get every half decade here. I go to my table, and there it is for 45. If you do this calculation out, you should get an infant mortality rate of 7.6 predicted. So we're predicting that the infant mortality rate was 7.6 per 1,000 in the year 1995. Now, I gave you every decade. You could probably go back to this source, which is the US Census, and you could probably see how close this prediction is, or this estimation, excuse me, is to the actual data. So now I want you to, now we're going to go outside of our data set. So instead of using estimate, we should be using predict. Okay, so use your regression line to predict the infant mortality rates for 2006. And once you do that, I want you to start working on your data. I'll check your results in a minute, okay? I don't. No, you can just put new batteries in. All I know is that this you can get this software. It's called TI-83 emulator virtual. You can try putting that into Google, or you could just use. I would suggest for today, Jonah, that you and Orlando just share doing the entry in. I don't, his it's not working. Okay, so this is what I got for my estimated rate. Does anybody get that? Okay, good. So now what you should do